ohmic heating. I think that the textbook does a good job of explaining this in the context of potential energy, but it's a fairly short explanation to come up with the P equals IV or I squared R ohmic heating. I'd like to justify this in terms of the microscopic picture that we developed earlier when we defined current. So we'll take our standard resistive element here. That can be just a cylindrical cross-section of a wire or a carbon resistor. So let's see where this heating comes from. We'll keep the cross-sectional area A, the way we've defined it in the past, and the length of this piece of wire, capital L. And what we want to do is pass a current say left to right through this wire. This will be a constant current or a DC current, I. And then we'll ask what is happening to an individual electron, one of the free conduction electrons, the free charge carriers in this picture. We have current flowing to the right. This implies there is an electric field vector pointing to the right. Okay, current flows from higher to lower voltage. Electric field points from higher to lower voltage in the same direction as the current flow. And we've talked previously about how current density, J, which is a vector that has magnitude of the current I divided by the cross-sectional area A. It's sort of an area density. If you take that and multiply by the resistivity, rho, you obtain the electric field in the wire. If the electric field is pointing to the right, then that electron will have a force, a QE force vector since the electron has negative Q, that force vector must point in the opposite direction as the E field. That is a constant force in time. We talked, of course, in class about how this is a crazy mosh pit of random motion for each individual electron bouncing around the wire. But with that current present, with the electric field present, there is a tendency, an overall average tendency to drift to the left for this electron. So we can add that drift velocity, Vd vector, have we defined everything we need? Yes. What is the overall resistance of this piece of wire to the flow of the current? The macroscopic resistance R is The microscopic resistivity, that's the property of the wire's material, times the length divided by that cross-sectional area A. And we will need our definition of the current in this microscopic picture, which was lowercase n, which was the number density of free electrons in this case. That's electrons per cubic meter. So the current is lowercase n, cross-sectional area A, magnitude of the electron charge, Q, times that drift speed, or the magnitude of the drift velocity. We can ask a simple question. How much work is done on one electron per unit of time by the electric field? If you recall from University Physics 1, the work done by a force is simply that electric force dotted with the displacement vector dl. And in our picture up here, you can always think of VD as defining the displacement vector dl. Their directions must be the same. The relationship, of course, is that Vd, the velocity, would be the displacement vector per unit infinitesimal time, dt. So how much work is done per unit time if we take a time derivative of this expression? Of course, our force is constant in time. What is the time derivative of work? That's the rate at which work is being performed. We call that power. So the power input to the electron by the electric field is d by dt Our force and our dl vectors are parallel, so their dot product will simplify to just the magnitudes multiplied by one another with a constant force. This is just dl dt, and that, as we defined earlier, is the drift speed. So we have that the rate at which the electric field is doing work on the electron is equivalent to the force times the drift speed. In general, you saw that in UP1, that the power input to your system was the force vector dotted with the velocity vector. Well, the power input by that electric field is QE, magnitude, the electron charge, times magnitude of the E field. That's your force. And we have VD. Let's rewrite this, taking out the QVD from our definition of the current, the product of Q magnitude Vd is simply the current divided by lowercase n area A, and the E field will replace with magnitude of rho J. Why did we do this? Again, we're trying to justify the power input by that electric field to our system, which is just one electron that we're considering at the moment. All right, rho J, we're going to replace rho with A times resistance over length. So this is rho now, AR over L. J magnitude is current over area. See, one factor of area cancels out. What we're left with is I squared R divided by lowercase n AL. Well, we have something that's starting to look like I squared R, ohmic heating. What is this lowercase n AL? What is AL? Well, area of the base of the cylinder times the length is its volume. So the power input here is I squared R over lowercase n volume. I'll just write volume so that we don't confuse with drift speed. And what is the number density of free electrons multiplied by the volume of the cylinder? It's just the total number of electrons sitting in this cylinder. So we've just considered one of those electrons for now. We have I squared R over N. This is the power which is input to a single electron. So the total power is simply the number of electrons times the power applied to one electron. And you can see that's simply I squared R. And that was our desired proof. Now, understand that this was calculated as the amount of power being input to that sample of free electrons. You need to take the next step and say, because the drift speed is constant, total kinetic energy of those electrons is constant, and we're led to the conclusion that the power input from that electric field must be exactly balanced by some release of energy, and that is the ohmic heating. If it was not balanced by this release of energy, the kinetic energy of the electrons would be changing, right? If this were taking place in free space, an electron feeling a constant force would accelerate to the left, and it would pick up speed, and its kinetic energy would increase. Because it's not happening in free space, it's happening in a wire, that drift speed remains constant, implying that all of the energy going into the system from the electric field is being lost to the ohmic heating.